In this video, we will be discussing the fully coupled atmospheric equations. So what this is doing is taking all the equations we learned and combining them in an effective way um, for the purpose of modeling the entire atmospheric system, including not just limited to each individual equation running by itself, but involving all the equations that we've learned to constantly update our equations over time. And in the last video, we discussed how to update pressure and temperature which was the final key ingredient that we needed to complete our system and to be able to update all of our variables so we can efficiently predict the future of the atmosphere. And I also mentioned in the future, I plan on discussing what I call the fully coupled atmospheric-oceanic equations, which will also include an ocean system in there. Um, and the main difference, the equations will be the same. The main difference is that the um, density and viscosity of water is different than air. But there's also some more complicated processes, which I don't know if I will be able to discuss, but I will briefly go over um, with those atmospheric oceanic equations. But for this video, um, first we have the momentum equation, which I used to call in previous videos, I called it the atmospheric equation, um, just because it calculates the wind velocity and how that changes, but it's also called the momentum equation. And so what we have here is we have du dt is equal to the pressure gradient force plus the viscous friction force plus the gravity force plus the um, Coriolis force plus the curvature terms related to the Coriolis force. And remember that for gravity, it's equal to this gm, which is about either 9.81 or 9.82 meters per second squared. And then we also have the centrifugal force. And I well, actually here I like to use in this case I'm trying to use only rho and not this alpha here, so that's not necessary. Um, So we'll notice that, for the centrifugal force, if we know the dimensions of our Earth and we have this, you know, um, know every point at our Earth, this R vector is just position. This is based on how fast the Earth is rotating and also the latitude that you are at. And that means that without even knowing any of these variables, we already know the gravitational force. And it doesn't change in time. It only changes in space. So that means we just need to, we're limited to a limited number of variables. So, to update U, what we need is density, the current density. So we want U for the next time. So we will have the current density, we need the current pressure, and the current velocity. And every other term here, u, v, w, that's the same thing as the velocity at the current time. So we can update u easily. However, we can update u, plug u back in, update u again, plug u back in, it's fine. The problem lies in the pressure gradient force and also this density term in the viscous force. We need to update these every time because as air moves, mass of air moves, and therefore density changes because density is mass per volume. And, the temperature and the density also affect how pressure is distributed in the Earth. And I also wrote some, um, you know, of these operators like the gradient, the Gaussian, the curl, how we can actually fully expand these equations. If we were writing this on a computer, we'd write it like this, and then we'd also, beforehand, we would set equal these first. That way we don't have to write out the entire thing, but as you know, this is actually a three-line equation, and these terms can get very, very complicated if you write out the full equation. So that's why we make it like this. So now, to update density, we're going to use the mass continuity equation. To solve that equation, we simply need to know the current density and the current velocity, just like in the momentum equation, and we can update this simultaneously. So that's great. But what we've been missing is pressure. How in the world do you update pressure? And so I talked in previous video, I derived this, and I believe using the equation of state, and I believe it is the way that um, it is calculated. Um, Also, there are some different coordinate systems that can be used. So here we're using X, Y, and Z. You can actually use a coordinate system X, Y, and pressure, and the pressure term from the equations will disappear basically. You won't have pressure. Um, but even in that case, the coordinate system, X, Y, P, X and Y are constant in time, but pressure could be changing in time anyways. So regardless, we still need to, for most cases, we need to update pressure. So we use the thermodynamics equation. So for that equation, we just need um, the current temperature, current velocity, and we need to make a parameterization, which parameterization for dq dt. And that is extremely complicated. And many times you can ignore this term. You could ignore this term, but obviously we have the sun shining. There's radiation changes all the time. Um, so but this is very complicated and kind of outside the scope of today, so I won't go into that. But as long as you know that, you'll be able to solve this equation. And if you notice, some of these are in gold. I did not make T gold because what gold represents is terms coupled with the momentum equation. So temperature, you know, is not in the momentum equation, but pressure is, and we do need this equation to solve pressure. So once we've solved an dt, and also I should mention, we do want to know the temperature so we can make a prediction of temperature. That's a separate thing. But once we get dt, we can also then use that to update pressure. As I talked about in the last video, we have an equation to get the future pressure. We need the current time density. We need this dt, and we need the current t. So this is the change of t. We need the current t, and we need the current velocity. Now we've updated pressure. So once we go to the second time step that we're integrating, we've been able to update everything in this equation. And then we can get U again. Then we need to update these again. Then we'll go back and update density, get dT in order to update pressure, and we're good. And finally, we want to know about clouds on Earth, which includes storms, because storms are also type of cloud, in a sense. Um, we want to know that. And what we've been ignoring is that air has water vapor in it. So we're also going to need to use the moisture continuity equation. All we need for that is to know the current U and initial the current velocity and the current water vapor. And this could be, QJ, you can do V, L, CR. There's a whole bunch of J's that we're going to need to check, vapor, liquid water, cloud, rainwater, etc. So this equation is actually going to be like maybe 8 equations in one, but we just solve it each time. And it's a pretty simple equation. Issue is this source sink term, exactly what I said here. We're missing we are missing the dq/dt term as well as this sj term. Oh, and also, yes, I should also make this gold because that is, I forgot to mention, there is a row right here. We also need to know the current density. This source sink term um, includes all the phase changes like condensation, evaporation, precipitation. It basically explains how Q moves between, this one. So Q could go from V to L. So you'd have an equation for V and you have an equation for L, but then the equation for L would include a term for V and C and R and how those interchange between all the water vapor equations. Um, Additionally, the temperature term itself and dq/dt are going to be affected by the release of latent heat and other processes like diffusion from the source term, from this Q, that will also affect this as well. So this is why currently weather models are really bad at getting, um, not really bad, but they're a little bit off, very off in some cases from the reality of a storm or something like that, is because we need to improve this term. And improving this term means we need to improve this term and this term. Currently, though, this momentum equation we know is very, very, very good. And of course, the only things that are keeping it, causing it to be off, is that our update for pressure depend on heating, which depends on water vapor. So there might be some small discrepancy in these terms. But as for predicting for for a short period of time, like 1 to 2 weeks, you know, 1 week is the best. It is extreme. The momentum equation is extremely good. So the state of our field now is really, there's climate, but one of them is really to fix this. Um, and of course, not just for weather prediction, that fixing this problem is also important for climate modeling because we want accurate weather prediction in order to see how temperature is moving around the Earth and things like that. Um, what else? I mean, another thing we need to do is have a coupled atmospheric oceanic model for global model, which is currently in the works. I think that's very important. Um, and also, um, I think there's some um, things that can be done to solve this term that might be less of the parameterization method, and maybe there's ways to get direct method for that. Um, the more that is expounded on, I think, the more we'll be able to predict what is the weather perfectly in our atmosphere, which is the goal. We want to prevent and mitigate and tell people in advance of severe weather, and to do that, we need to solve these equations. But another thing is we can understand and predict how the universe functions um, as well. That's kind of the two main goals of atmospheric science, I would say, personally. So to summarize, here is how we do it. And you'll note that we have a very limited amount of variables that we actually need to know. We just need to know density, pressure, velocity, temperature. Um, that's it. And also heating. Um, and that's everything that we need to know to, as well as this as the source sink terms. So just again, we have we need to know density, pressure, um, velocity, and the heating terms, and we can update everything like velocity, pressure, density, and we can also understand how water vapor is distributed within our atmospheric system. So to recap, we first start with the momentum equation. So number one, we use the momentum equation. And we need the initial density, pressure, and velocity. And that equation will update only velocity for us. And so the star means what we need to update and see, this is updated almost immediately. Um, then number two, the mass continued equation is solved given the initial density and velocity to update pressure. So we've just completed this, what we need to update. That's what the stars mean. And then we use the thermodynamics equation using the initial T, initial velocity D, and the heating source term, heat source sink term. And that will give us two things. Number one, it'll give us dt dt. And number two, it will give us temperature, updated temperature. So we can, you know, predict the temperature. It's another nice thing. And then number four, the pressure equation, as I call it, we'll need the initial density, initial temperature, initial velocity, and this dt dt term from the thermodynamics equation, and that will give us an updated P. So we've completed this update here. And finally, we're interested in how moisture is distributed because the moisture tells us how these terms, dq, dt, and dt, dt change. So we will use the initial um, water vapor amount and the initial the current velocity, sorry, current water vapor, current moisture amount, current velocity, and the source sink term of the moisture continuity equation to update the moisture. And that will complete our entire system. I also want to mention two more things, which is we've also done one thing is we forgot to mention is this equation is incompressible. So it's actually better to use this for something like water, and it's a approximation for air, and it works pretty well. But I think maybe the pressure gradient, I'm not sure, but I know for sure this friction term needs to be a little bit different if we're going to say it's compressible. Um, and we'll have the original friction term plus another term, and it has this weird gradient of divergence term, where mu is the viscosity, we call it shear viscosity, but then we also need to know bulk viscosity. However, this term is very, very small, so that's why usually we just completely ignore this term in order for it to, and the air will still be compressible. Um, um, and I think another thing is this bulk viscosity term is very hard to calculate as well. Um, and additionally, for the gravity force, we've assumed that gravity is constant everywhere on Earth. And this is usually negligible, but there is an effect of terrain. So if you're at the bottom of the ocean and you're by one of these absolutely gigantic, ginormous mountains underwater, some of them actually have higher gravity. But the amount of higher gravity is in like, it's decimal points down. It's like 0.000 some, some number here in this place it's being changed. And so we honestly don't really care about that because usually velocities are something like 1 meter per second or 10 meters per second. Maybe it's 40 meters per second at the very highest. So we don't really care about such a small decimal, so we usually ignore this. But if we were wanting to be absolutely perfect, we I don't really see a point, but what you can do is you can say you want to get a better GM, and you can use the fact that this is equal to the negative gradient of the potential, the gravitational potential. So I'll write that gravitational potential. And I don't know too much about this, but I found it on Wikipedia um, that you can find geopotential by solving this equation here. Um, that is the Laplacian of geopotential in space, so x, y, z, and time. Though I don't I don't see why this would actually change in time. So um, the geopotential, well, actually, yes, so the geopotential would change in time because, well, actually, technically, no. Technically does not need to change in time. So I'll just fix that. I mean, technically over like a millions of years, maybe changes in time, um, but not really necessary. Um, the Laplacian of this gravitational potential is equal to 4 pi times the gravitational constant times the mass point density. That's basically like how much mass is accumulated in area. So if you have this large mountain at the bottom of the ocean, this M would be really big, way bigger than normal, and that would have a very small kind of increase for when we solve this Laplacian, it will, slightly increase GM. So yeah, Laplacian will likely get rid of most of like the high number here. So, but it will be slightly higher gravity if there's more mass in a certain area. Um, and yeah, that'll be that. So in the next video, I hope to discuss basically a basic way of coupling an ocean and atmospheric system, and also explain that there's some other things kind of missing with that, and just kind of talk about the basic way that that's done. Um, and yeah, so stay tuned for that video. And I hope you enjoyed this one, and have a good day.